This conference will now be recorded.
Right, okay, so building a new railway is a major undertaking, and there are many considerations in the feasibility stage before it can be deemed viable. So finding a corridor is an early activity to support a business case. Governments and other clients, such as developers, will not embark on a project incurring significant cost until the business case and social, environmental and economic impacts are studied. So the rail alignment is only one aspect of any feasibility study, but it plays a crucial part because it's the backbone of the scheme from which many other aspects depend. So key considerations such as passenger demand, journey times, frequency of railway services, and the overall capacity to move passengers and or freight between geographical centres. It depends on having a rail alignment and an outline track layout to study. So once the initial corridor is established, and this is an important point for me, it's often common that for a project to be locked in to this, except for relatively small minor adjustments, improving the alignment within the corridor width in the following stages before construction. So therefore, the initial corridor evaluation and selection is an important task, and investing time and money at the start is often a precursor to a successful project outcome further down the line. So this is about investing more time in the early stages of a new railway rather than just doing a line on a paper, which can lead to trying to resolve lots of problems later on further down the line if it's left to go along too much like that. So moving on to the next slide. This is not working. Right. Okay, so first of all, corridor study requirements. The initial corridor study relies on finding an alignment which four things really: satisfies the minimum geometrical requirements, has few conflicts as possible, serves suitable intermediate and terminal stations, and keeps civil engineering costs to a minimum. So finding the most cost-effective path through the topography and following existing transport corridors is generally a common starting point. But in the case of high-speed rail, the geometry of existing highways and railways are sometimes difficult to follow due to the flat radius curves necessary for for high-speed operations. So heavy haul freight lines, they have their own requirements as they are subject to relatively shallow gradients and vertical curve restrictions necessary for the traction of long freight trains with high axle loads. Metros and light rail projects generally, because of the slower speeds and more relaxed geometry constraints, it's common to be able to follow highways and roads into city centres to avoid expensive tunnelling and subsurface stations where possible. So building a rail corridor that is alongside the highway and sometimes between the carriageways in the central reservation is a popular metro approach, which you will see in many countries across the world, many cities. So in terms of preparation, it's good to have some investment in the latest technology available for finding the lowest cost path through the terrain. It can potentially save substantial capital costs. So modelling alignments across the virtual terrain with the capability of overlaying good quality digital mapping is considered to be best practice for initial corridor studies. So as a rail alignment engineer, it's important to have a team with rail alignment experience and capability and get the support from the team of specialist engineers. So specialist engineers, all part of the team, would typically include survey engineer, environmental engineer, geotechnical, hydrological, highways, tunnelling, structures and utility engineers. And also it's important is local knowledge. And so having access to information on land use, politically sensitive areas, and any plans for future schemes that may impact on a chosen corridor are key considerations. So corridor exploration will lead to an evaluation of options, and this is typically carried out as a multi-criteria analysis, which considers the following: engineering, capital cost, journey time, operations and maintenance, constructability, and environmental factors. It's important to consider how the mapping and terrain models can be sourced very early on, as this can take time to arrange. In the UK, there are excellent mapping resources and ground surface models available from Ordnance Survey, local authorities, but this is often not the case in other countries. To find an initial corridor, the mapping, imagery and digital terrain model can be purchased commercially through a satellite survey and imaging supplier. For example, if a corridor has a chosen study area, which is say 25 to 50 kilometers wide, then this will be a vast amount of data if it's and too large for some software applications if it's too accurate. So at an initial stage, it's acceptable for the resolution to be a network of survey points, which are say 10 to 20 meters apart with height data to an accuracy of 0.5 to 1 meter. This sort of terrain model accuracy will allow a first pass at finding low-cost corridors to study further. So when an initial corridor evaluation has taken place and a corridor is selected, it's common to narrow down to the study area to say a 1 to 5 kilometer wide corridor. The selected corridor requires more detailed mapping and a digital terrain model with sufficient accuracy to design a rail alignment and calculate cut and fill volumes. So typically at this stage, a LiDAR survey would be arranged, sourced from a specialist supplier who will carry out dedicated flights using light aircraft, helicopter or drone technology to survey the narrow corridor. The benefit of LiDAR surveys over satellite surveys is the greater accuracy and the ability of the data to be manipulated so that tree cover and vegetation can be stripped out to create a model of the bald ground surface. So using model applications, so railway alignment design software applications are used to create alignment strings in model space that are geometrically compliant with the chosen limiting values. At the feasibility stage, these strings will represent the center line of the rail alignment, from which individual track alignment center lines can be developed at a later stage when the chosen center line is relatively fixed. So a lot of people will be familiar with Bentley Open Rail Designer, which is the latest Bentley rail alignment software really, which is taken over from Bentley Power Rail Track and Bentley Rail Track. Open Rail Designer is now being used widely for alignment designs, and on the right is an image from Open Rail. And I've also, just to cover 12D, which is another software application used quite extensively in Australia as an alternative. But these kind of tend to be the two main rail alignment software applications. So when a ground surface model is supplied from the supplier, it will be thousands of points, with each point having a set of three-dimensional values, i.e. a northing, easting and height value. These points, they need to be well, actually filtered out so that there's a manageable number, and then triangulated into a net to represent the ground surface, so that when the alignment strings cut through the model through the ground surface, their height can be determined relative to the net or ground surface, either above or below the virtual surface. So that gives you possible to then calculate cuttings and embankments, that sort of thing. So just want to cover here the use of specialist software applications. So these applications such as Trimble's Quantum, they're able to analyze thousands of alignments and rank them in the order of cost to allow options to be shortlisted. Quantum will simultaneously consider environmental, community, cultural heritage and hydrological impacts in parallel to considering the crossing of linear features, wetlands, floodplains and geology. It's effectively a one-stop shop where the model is loaded with all the data of all the necessary inputs, and then it will analyze the cost of each alignment, allows selected alignment output strings to be exported into other applications, you can shortlist alignments. You can get the top 10 alignments in terms of cost, and then do an appraisal on those, for example. So on the right hand side here is an image of Quantum. As you can see, there's lots of colored strings in there which represent lots of different alignments, which are going from point A to point B across the terrain. In terms of just using manual techniques, not specialist software, it's possible to find a pathway through the terrain using a number of techniques. So these are two here. So assigning colors to a particular height band so that the elevation increases with the contours of the terrain. The color gets progressively darker or changes color the higher the area. So this makes contours easy to follow. So this top image here has got some orange dotted lines either side. That represents the limits of a tunnel, and this black line is an alignment, and it's coming out of the tunnel and following this sort of orange band, which kind of maintains a particular level. And so you can see visually in plan where you're going with this in the sense of the contours that you're trying to find the best route through. The second example below is where the model can be rendered in 3D, and that allows you to sort of turn the model around in model space, and then it gives you a good visual view of where an alignment can go. It's more a sort of a more manual technique, that one. Okay, so touched on earlier technical parameters. So this is particularly one area that we need to consider very early for whatever railway we're considering. So first of all, this slide is looking at high-speed lines. Typically, minimum curve radii and speeds greater than 350 kilometers per hour are typically going to be between 7,000 and 8,250 meter radius curves, depending on what speed is used as the upper limit. Exceptional limits can be lower, but this should be avoided at the feasibility stage, really, so that you've got some sort of comfort, sort of margin of safety, really. If a project wants to future-proof for a higher speed that is in excess of the chosen operational speed, then it just needs to be considered that the radii will need to be flatter, and this of course constrains the alignment further, and that constraining will have an increased cost. So there will be a cost implication to future-proofing for a higher speed. And when it comes to looking at suitable cant and cant efficiency balance ratios for high-speed lines, ratio is often around 65 to 75%, which is a higher ratio than on slower speed railways, which very often these days depend on higher cant efficiency values. but when you're up at the high speed end, cant efficiency does need to be modest compared to other railways. And we've got some little images here which kind of show you a little bit about how cant efficiency can vary depending on the cant, on the applied cant. So the first image shows you where the centrifugal force, which is the force which is wanting to move the vehicle outwards laterally, when that's balanced against the self weight of the vehicle, the resultant force, when it cuts the midpoint in the forefoot between the two rails, that's considered to be the balanced condition with zero cant efficiency. And then as you go faster, the centrifugal force increases. So therefore the resultant force starts to move out towards the high rail. And as long as that resultant force is within the high rail, it's still being controlled. It's a level of cant efficiency which doesn't exceed the limits. But when in this third image, the resultant force is tending to go outside of the high rail, this is where the vehicle will want to derail. The flange of the wheel won't let it until it really gets high, at a point where probably the vehicle would roll over rather than just come off. So so a little bit about cant efficiency then. So moving on to the next slide. Right, this one's about heavy haul lines. So the technical parameters for heavy haul freight lines are somewhat different. So there's a balance to be struck if lines are built to be mixed passenger and freight lines. So there's a balance in terms of cant and cant efficiency between the two. In countries that rely on freight traffic being up to 2 kilometres long, very, very long freight trains, and in some cases using double stack containers, with typical maximum axle loads of 32.5 tonnes. This all has to be assessed because the geometry limits can be set to suit the, they do need to be set to suit the tractive effort of these very long and heavy trains. So typically gradient limits are much flatter than for passenger lines, and restrictions are placed on vertical curvature where the longitudinal profile rises and falls within the length of the train. So on the right here, we've got an image of a vertical alignment showing the freight train which is straddling this vertical alignment. It's ducking and diving under some structures. It's limited to only 1%, which is quite a flat limit, but it's necessary. This particular alignment is right on the limit for particular 2 kilometre long double stack container freight traffic. So so very, very different set of technical parameters that have to be worked for freight. When we look at metros and trams, it's completely different again. The technical parameters for light rail are different and can vary significantly between light rail, metros and tram systems. On many tram systems, the circular curves join the straight sections without transition curves, so virtual transitions. And allowable cant efficiency limits are high to keep the cant as close to level as possible, particularly in street running situations. So allowable horizontal curve radii limits on tram systems are circa 150 meters desirable, but can be as low as 35 meters on embedded track. And switches and crossings can be even smaller, 25 meter radii. And there's an example there on the right of a tram turnout showing a 25 meter radius. So there's a slide here on vehicle gauges, because for new railways we need to understand the gauge separation of tracks, how wide we need to allow, how high crossing points need to be. So overhead catenary systems need to be allowed for, and this needs to be considered as well in the gauging envelope. So I've got some examples here. the GC gauge, which is a very common European gauge to be used on new passenger lines, and the standard AAR gauge, which is USA gauge, again a very common passenger gauge that's used around the world. So the image on the left-hand side is passenger lines, and then on the right-hand side we've got the composite AAR gauge, which is often used for double-stack freight containers in lots of countries around the world. So environmental considerations, very important for new railways, and these would typically be identified in the mapping data in the study area. The environmental engineer would work on this and provide this as an input to the model for the alignment development. And typically, you would there would be a environmental model which would have different layers which you could turn on and off, and it would show things like protected forests and woodlands, wildlife conservation areas, heritage sites, sites of religious interest, and then city urban conurbation and industrially developed areas. And this is an image just to give you a sort of an idea of the different types of environmental layers you can get in a typical GIS application. So environmental considerations then, I've mentioned forest and woodlands, and this is a very sensitive subject, and any project needs to plan for the coexistence of the railway and its natural surroundings so that it's managed in future maintenance schedules. On some projects, green cut and cover tunnels are provided to minimise the impacts. Wildlife conservation, avoiding the habitat of protected species and accommodating seasonal migration paths of animals and reptiles cut off by the new railway, unless they're created by providing underpasses below the railway. So these have to be considered. Sometimes an environmental engineer will have particular requirements for crossings under or over the railway. And for example, in the Middle East, it was common to provide camel crossings where ancient trails are intersected by the line. And these camel underpasses, they needed sufficient headroom for the tallest camel, so rail elevation is important in these points. Heritage sites, cemeteries and burial grounds fall into this category and are sometimes difficult to identify without site visits or local specialist mapping resources available through local authorities. And sites of religious interest, churches, mosques, synagogues, temples, etc., they're all sensitive to noise and vibration levels from the railway, and measures become more expensive the closer the line is built to the receptors. And also in this category, for noise and vibration, theatres, hospitals, laboratories, cinemas are also where noise and vibration mitigation is required. In the city and suburban areas, and the urban sprawl of large towns are sometimes impacted in some way. A railway passing through a town or village can potentially put a social barrier that changes the dynamic of the area. So that has to be taken into account if the alignment has to pass through a particular town or village in some way. And in urban areas, light rail systems typically follow the highways and the heavy rail, and high-speed rail often has to be a tunnel beneath residential areas if the impacts are too great. So a couple of slides on geotechnical and geological considerations. So first of all, geological engineer will be out seeking geological data for the corridor, and thinking about how that data can be assembled into geological zones. So a bit on that, a bit more on the next slide. Then some of the tasks that they have to do is look at the cut and fill suitability, tunneling, any tunneling avoid zones due to poor ground conditions, and any general poor ground conditions in any of the areas. So the geological mapping information is quite important to be able to compare that to where the alignment's going. And this image I'm showing on the right here is some mapping in Google Earth, and this is HS2 actually, and the red line through here is sort of HS2. You can see where it's crossing the light green. There's a black section to it at the lower end, which is that's the Chilterns Tunnel going through the chalk. And right at the bottom end, there's a blue end there, which is Colne Valley Viaduct, which is a crossing, very tall viaduct crossing the valley. But the good thing is you can download this British Geological Survey as a KMZ, a KML, from their website, bring it into Google Earth and just switch it on and off as an overlay. And then if you've got your railway lines or your own alignment showing in Google Earth, you can compare it to the geological strata that it's crossing. Okay. So geological zones, it's good practice to create these because they group together geological conditions that have similar levels of risk and suitability. So what this particular project example shows is the 4 zones, which kind of range from the sort of the soil and rock with good bearing capacity in zone 1 through to the zone 4, which is sort of the high sensitivity areas such as lakes, springs, flooding, floodplains, and that sort of thing. So by color coding the 4 zones, it allows the alignment to easily navigate to the good zones and avoid the bad zones. So it's quite a good technique to use when considering the geotechnical considerations at feasibility level. Okay, I mentioned earlier about cut and fill balance because that requires a geotechnical assessment. So material cut from cuttings, it can't always use as fill for embankment construction, and rock blasted from tunnel construction, for example, may have explosive material mixed in with the debris. So 100% of the volumes removed cannot always be assumed to be suitable for embankment construction. So typically you wouldn't use all of the cut for the fill. There would be a percentage according to the geotechnical engineer would make an assessment of that. So geology and hydrology conditions are a major area of consideration. There's a poor choice of corridor alignment can have serious implications for capital costs and project feasibility, as well as ongoing maintenance costs when the line is built. Optimizing the vertical alignment can help in areas where landslides and flooding are a risk. So selecting a corridor where there are poor ground conditions can result in expensive piling, and in some cases, such as tunneling in collapsible soils, such as gypsum, it should be avoided completely. Sometimes poor ground conditions cannot be avoided, such as in coastal areas, wetlands and marshes. The rail elevation in these areas is important to be sufficiently high to spread the load to minimise the need for expensive piling, depending on the stability of the subgrade below. So, for example, railways are successfully built and maintained on peat and coastal sabkha. What sabkha is a sort of a crystallized, crusty sort of sand, which sits above a sort of softer material underneath. So you can build on that, but the first consideration will be to avoid it if possible. So hydrological considerations, many countries have seasonal events resulting in significant surface and groundwater flows following heavy periods of rainfall, particularly in hilly and mountainous areas. So these can be in areas that remain dry for much of the year and are not easily identified from mapping and terrain models without the expertise of a hydrology engineer. So building railways across streams and rivers has to consider worst case water flows, flooding and tidal waters. So modelling the extreme conditions is necessary before rail elevations are fixed. So where the rail alignment potentially cuts through watercourses, these are not always apparent, but at low points in the terrain, pipe culverts and box culverts are necessary where the alignment crosses the watercourse. In these areas, a suitable rail elevation is necessary to provide adequate clearances for culverts to be built with sufficient cover between the track system and the top of the culvert. So highways considerations. We mentioned before that new railways do tend to try and follow highways corridors, but this is a bit of a health warning if that's the case, because you can get caught up in these big sort of cloverleaf intersections with at the junctions of motorways and highways. So so this is an example here in the image where there's actually, if you look closely, there's two railways crossing this road intersection. One is a metro running parallel with the highway, a main highway, and then at 90 degrees to that, there's another freight railway running underneath that one, and everything's ducking and diving, so it's really complex. So I would warn to try and avoid getting involved in this sort of thing if at all possible. Another feature is that that you always need to consider crossing minor roads, but in some cases, some minor roads can be constructed to go over the top of the railway, and that enables you to keep the railway to a sensible elevation without having to go up and down over road crossings. So a slide on utilities, because it's quite common that new alignments will cross or come close to overhead power lines, for example. The pylon structures are usually easy to identify in the mapping imagery if it's good quality, but site visits are usually needed to confirm the transmission corridors and assess wire heights before they're surveyed. Sometimes it's beneficial to position the alignment relatively near the pylon structure, maintaining sufficient clearances so that the overhead clearances are maximised. So what this is about is that if you were to place the alignment at mid-span, the sag of the wires between the pylons is likely to result in the wires having to be lifted. So sometimes it's better to offset the alignment away from mid-span. So oil pipelines. So where there's oil pipeline crossings, it's often not possible to divert these without considerable expense. So rail elevations will ideally pass over these. It's not normal to build these into embankments, as they need separation from any part of the railway that will cause them to vibrate. They're very sensitive to that. So structures are needed to maintain this separation, and horizontal rail alignments are normally adjusted to maintain a sufficient distance from the pipelines that run alongside the proposed rail line. In some locations, high voltage cables are buried, and where the rail alignment intersects with these locations, it's necessary again to provide structures to pass over these utilities. The cables require maintenance access, and this includes maintenance vehicles. So clearances for maintenance vehicles will affect the soffit height of the bridge and therefore the rail elevation. So moving on to engineering a path through the terrain and into urban areas. So when selecting an alignment, both horizontally and vertically, it's necessary to understand the relationship between the two. There is a maximum height above the terrain, beyond which the alignment becomes uneconomic due to the capital costs involved in building high viaducts. Therefore, in some cases, horizontal alignments can be driven to taking a very different path in order to satisfy vertical alignment limits. So it's important to consider the vertical alignment before it's deemed feasible. Yeah, reason I say this is because it is very common in the feasibility stage for alignments to be considered only as a horizontal line on a map. In some cases, you can get away with that, but in other cases, it's risky to do that. So in fact, when you're considering alignments, particularly through hills, valleys, and mountainous areas, the vertical and the horizontal alignments cannot realistically be considered separately. They have to be considered together. So first of all, I've got a slide on vertical alignment. We're starting from sort of open ground where there's no features around really. You've got a ground surface that's generally flat, well away from crossing points. A standard cross section will typically apply with a rail level at approximately 1.2 meters above ground level. This is a minimum height necessary to ensure that the formation under the track bed can be drained naturally to the surrounding terrain. In some locations, such as in desert regions, the rail elevation is placed higher to help mitigate against wind-blown sand. And in other situations, such as where there's underlying soft ground with a reasonably stable upper surface, the rail level is elevated to spread the load and avoids disturbing the stable upper surface. So where the vertical alignment passes over culverts, there are minimum heights required to provide sufficient cover, and crossing highways, minor roads, railways, rivers and streams. Again, there are minimum clearances. Structural depths of bridges and track system need to be taken into account as well. Where an alignment crosses valleys and depressions in the landscape, the railway will initially be on embankment until the height of the embankment reaches a limit as determined by the geotechnical assessment of the earthworks and underlying geology. So beyond this point, viaducts may be necessary. And again, viaduct heights above the valley floor should ideally not exceed around 30 to 40 meters. I would say 30 meters ideally. Although some viaduct examples are anything up to 70 meters high, but these are very exceptional structures, very expensive to build and should really be avoided. So the image on the right there is the Millau viaduct. It's not actually rail, it's a highways, but I've shown that because that's probably one of the highest viaducts in the world. It's 70 meters high, and in southern France. And yeah, you can see this is an exceptional structure. Don't really want to go there. So got a slide here on rail expansion devices. It's a little bit of a hobby horse for me at the moment, this one. So when you're considering viaducts in an alignment, the viaduct length is not critical to the alignment, except the fact that any continuous viaduct that exceeds 100 meters in length must consider the need for rail expansion devices in association with the structural expansion joints. Now, rail expansion devices are quite common, but from a design and maintenance point of view, they should be located on straight sections of straight and level track where possible. And the reason this is a bit of a thing for me is that so often I've come across alignments that have not taken this into account, are curved, and then when you start to further down the line, you kind of realize that actually you need high cant and high cant efficiency on the curved sections. And if you're placing rail expansion devices in those locations, it really is a major risk to maintenance to put these on high cant deficiency areas. And if you can see this photograph here, it shows you the REDs. These are the type that's required that cover the lengths of expansion that are necessary that go along with some of these long viaducts, and they have like a switch and a stock rail. And when you think about facing switch and the risks of derailment on that on heavy curves, it's really something to be considered. So I would say that in feasibility stage, you could use this little diagram that I've got here, which is to consider whether a rail expansion device is either on one side or both sides, and also on the very long viaducts that they do, is necessary to have them in the mid-span, in the middle on an inert span, and there could be more than one of those if they're very long viaducts. So it's about actually trying to provide a section of straight track where these REDs are going to be located, and that's the message I really want to get over there. Okay, vertical alignment then, cuttings and tunnels. In areas of hills and mountains, cuttings are inevitable and tunnels are necessary, but where the maximum cutting height is exceeded, or it starts to become uneconomical due to the footprint of the cutting area, depending on the geology of the area, the cutting slope angle is determined by the geotechnical engineer, and this may result in putting benching or steps in the cutting face to manage the risks of landslides and rockfalls. Cuttings deeper than 30 meters often take up so much corridor width due to the slopes and the benching that at this point a tunnel becomes more economical. This is particularly the case where two single bore tunnels are assumed, which need to be separated at the portal by say 2.5 times the tunnel diameter, which is quite a big footprint, you know, and it has an impact on the adjacent cutting width. Okay, track layout now. Then I just got some typical examples of junction layouts. And so on the left-hand side is what most people are familiar with, the traditional flat junction with the diamond crossing. But at the top of the images, the flat junction example there is a more modern, the new railways junction layout, which will allow parallel running so that trains can pass going on and off the branch at the same time. And this is providing crossovers with some separation between S&C units. So on ballasted track, that's good for tamping and replacing units. And also the image below is the grade separated example, which is more expensive, of course, because you've got more civils, earthworks, and a structure flyover. But it does, from an operational point of view, remove conflicts, and is very often on high-speed lines is very often the norm. So there's a number of examples there, but it's the right-hand images really which I would recommend for junctions. So other switches and crossings and depot constraints, just to point out that on main line alignments which run alongside depots and yards, it should also be restricted to a maximum of 0.2% gradient or level if the depot is connected to the main line at both ends, in order for the depot tracks themselves to be level or subject to a maximum gradient of 0.2%. So this is where the depot of the yard is having an impact on the main line geometry before you've probably begin to sort of think about what the depot layout looks like. Other alignment constraints can be due to the track layout. Switches and crossings should be located on straight sections of track so that junctions, passing loops, station throats, perturbation crossovers, and depot access connections, they all need straight sections of alignment with sufficient length to position the S&C away from horizontal transition curves, vertical curves, and adjacent S&C units. So Other considerations which have an impact on this are the requirements to provide separation between underlying structures, under bridges and S&C. So what this is all really leading to is that if you've got a number of S&C units, there's a number of considerations there which could dictate the need for quite long straight sections of alignment. So, so all of these are constraints which relate to the position of S&C, and so therefore technical standards, suitable standards need to be developed quite early on in the feasibility study in order to fix these parameters. So a slide here on stations, horizontal and vertical alignments. Well, in terms of vertical alignment, we typically have station platforms are designed to be flat, or at least limited to 0.2%, and nominally positioned on straight horizontal alignments. In terms of track layout, the image at the top is a typical sort of high-speed intermediate station layout, where the two middle lines are through lines which would fly through at high speed, and then the impact of those high-speed trains is not affecting passengers standing on the platforms because the platforms are on the outside. So then further down, we've got a typical 4-platform terminal station layout. So this is just a typical metro type terminal station. And then on the right is a tram stop station where you would have just simply one turnout, which the points might be spring loaded, where a tram comes into one platform, trails through the points, and then sets back into the other platform without the points needing to be operated. They're operated by the wheels of the tram. And then lastly at the bottom, there's a typical 6-platform terminal station layout. And what you can see, the crossovers on the left and the 2 turnouts going to the right of those would get a lot of use. And so therefore, if there was any fault or problem and those points had to be clipped to normal, then you've got other S&C units such as the scissors and the other 2 crossovers shown in blue, which would allow you to use at least 4 platforms in a situation where you've got problems. So nobody likes having the scissors and the diamond in the center, but this wouldn't get much use normally, and would generally only get used in perturbation situations. So that's the logic behind that layout. Yeah, this is related to stations, but sometimes it's very, very difficult to get an alignment into a city area. You're sometimes following roads, and in some cases you can't go above the road, you've got to go underneath, and in some cases the roads are too narrow. You have very tall buildings on either side of the road with deep piled foundations. And this is just something I wanted to share, which was I've seen in a number of projects now, and I've actually seen these built. So this is a situation where you go from your 2 tracks into what looks like a single line, but it's not a single line. It's 2 tracks stacked one on top of the other. There's no S&C involved here, and this allows you to go underneath a very narrow corridor underneath the road. And you end up with a station often, and I've seen this a couple of places in Kuala Lumpur, where platforms are on different levels in order to cater for that. Okay, so finally, site visits, and just to cover site visits, because these are important, but I just wanted to mention that it's important not to fly out there and look at sites too early. It's always good to get some options developed before you go out and look. And that what you can do is your initial alignment options can be exported and into Google Earth or Google Maps, and then you can put that on your phone, and that allows you to go out on site and see where the alignments actually are on the ground. I just think that's a very simple sort of tip, which is useful to do. Okay, so just sort of to conclude the presentation then, so this commentary is based on experiences I've drawn from a range of studies for high-speed rail, heavy rail, metros and tram systems. So it's written to give an overview of some factors to be considered when rail alignments for new railways are being developed. And it draws attention to the differences in standards and requirements between the various traffic types and rail systems, climatic and geological conditions, and the local political and environmental complexities as well. So, so yeah, if we compare how the railways were designed and built in the Victorian times to now, simplicity has kind of given way to complexity in many areas, with the success of the railways and the innovations that have given us one improvement after another. So this progress has brought us higher speeds, shorter journey times, more train paths for greater capacity. And we as engineers, we must play a part in being comfortable with that complexity to facilitate that progress. So, so I've got a little quote here from Confucius. This is 2,500 years old, this quote, and it's quite popular. Life is really simple, but we insist on making it complicated. So yeah, I would agree with Confucius that sometimes it's better to keep it simple, as it's often true. What they say, the best ideas are the simple ones. Although it's an engineer's want to have a thirst for simplicity, but for the sake of progress, it's necessary to drink at the bar of complexity. So that's really my final comment. And I don't think we've got much time left, but if there's any questions, I'd be happy to answer them. So thank you very much for listening.
Phil, excellent presentation. Thank you very much. Very, very informative. Rail alignments for new railways. We covered a variety of topics: 3D modelling, CAD deficiencies, technical parameters for heavy freight. I certainly learned something new. I've got a couple of questions that I'll read out from the chat. Andrew Cornish has asked, with the new railway design, what are the considerations for maintenance teams to access the track? Thoughts about putting a road access alongside the track, for example, are in short supply along a lot of newer tracks.
Yeah.
So what are your thoughts on that, Phil?
Yeah, it's a good question, because some projects do provide a road which runs alongside the railway, and in some cases it's on one side, other cases on both sides. I think, you know, often when you're looking at an initial corridor feasibility, it's better to try and provide a little bit more width in the study for the corridor width, because you can always reduce the width, but it's very difficult to go the other way. So you know, I personally would take that approach in the early stages of the project, but there's always going to be a cost assessment of that, a value engineering assessment, which might look at it hard and say, well, do we actually need to run alongside the railway all the way, or can we deal with having access points, let's say every 5 kilometres and at key junctions, S&C? So yeah, there's no one answer to that question for all projects, and it really does come down to individual projects looking at their requirements and the nature of the remoteness. Typically, like in Australia, you probably would have a road running alongside the railway all along for miles, but then in built-up areas, it wouldn't be the case at all. So unfortunately, there's not one answer really, but I think it's every case has to be taken on its own merits, you know.
Okay, and Jordan Fulton has asked, the question was on the tip of my tongue as well. Jordan's asked, I'm sure there are many issues, but any specific alignment challenges that stick in your mind?
Yeah, well, there's been many that stick in my mind. Yeah, there's one on my HSR, the Kuala Lumpur to Singapore, where I spent a lot of time trying to get an alignment right to miss a water tower, because I felt it was important that this high water tower perched on the top of the hill, that the alignment didn't go right through the middle of it. And then we went for some time with that alignment, and then it came out quite later that instead of going through that, we went through the back garden of some politician who said, I'm not having that, you need to move your alignment. And I said, well, the only place you could put it is through this water tower. And they said, well, don't worry about that at all, just put it through the water tower. So so yeah, I think there's lots of little stories like that where you kind of make a decision yourself. Is what you think is best, and there's always somebody who's going to also put a spanner in the works. So so yeah, there's probably a lot of other examples that I just can't think off the top of my head, so I apologise for that.
What about the biggest challenge, Phil? If you had to, one particular project which offered the biggest kind of challenge for you, is there one that sticks in your mind?
Well, I think it has to be a Brazil project, because there that was feasibility for the high-speed line between Rio and Sao Paulo, and taking in a new alignment from the Baixada Fluminense, which is the flatlands of Rio, which is most of Rio's the sort of regional area, is only about 1 or 2 meters above sea level, with a number of hills. But then as you get to the back of the sort of the plains, if you like, you've got mountains there, which shoot up to 400 meters above sea level. And getting an alignment up into the mountains was really incredibly difficult. And there were previous projects which snaked around using radii that was really sort of tight and slow speed, and to use that for a high-speed line was just not practical. The journey time would have been the whole project wouldn't have flown at all because of the journey time. So we had to try and find some way of using maximum height viaducts and then going into the face of the mountain with a very long tunnel. So that was very challenging, finding the best alignment to do that. So I'd say that was probably my biggest challenge.
Okay. There doesn't appear to be any other questions, so I can deduce, Phil, your presentation must have answered all the other potential questions, so thank you for that. If I could ask Jordan, if you could just perhaps unmute and just give the vote a thanks, please.
Yeah. So Phil, thanks very much for taking the first step and presenting to us. Been really interesting, and I think for the first meeting we've had a really good turnout and some really positive feedback. So being the first person is always very difficult, but I've certainly enjoyed it, and hopefully the people that are on can spread the word, and we can generate further interest. So thanks very much for committing and doing that. Great.
Thanks very much, Jordan. Yeah, and thanks to everybody for listening. Yeah.
Excellent. And just a final thank you from me, and a gentle reminder, our next virtual meeting will be on Tuesday the 13th of October, 2:30 start, and it'll be map whiting, design tamping versus computated tamping, and also an insight into the Kiro K1250. So thank you everyone for attending, and hopefully see you soon. Goodbye.